Uh, Rayleigh-Taylor instabilities is a term that applies to when you have two levels of liquids or gases that are of different densities. And if the lower density is on the bottom, well, then it will try to get up. Like a mushroom cloud is the best example. A nuclear explosion, mushroom cloud. That this is hot, and so it's expanded way out compared to the cooler air. And so it rises up, and the cooler air is trying to rush down, and it comes in like that. And so I want to show how it applies, how I spotted that it applies to strata, limestone and sandy limestone strata that were not fully lithified. And I saw the effect while hiking. And so first of all, the term, I want to show this first so that you can look it up. There it is. Wikipedia has a real good read on it. So the purpose of this video is to apply it to solids or somewhat solids, non-lithified kind of clay-like material that can liquefy during an earthquake. It's called liquefaction. So let's look at it in the layers that I saw, and I'll show some pictures. First of all, here's this. Yes, I put that text on there. So anyways, when this asteroid hit, it created huge amounts of breccia, some mega breccia as big as houses. And the area up at Alamo, I'm talking about Alamo, Nevada. It's about 100 miles north of Las Vegas, Nevada. But that area is right on or very near what would be considered the crater rim, which they can't find the exact crater now. It's been too long. But it's right in that same area, not in the crater, but like very near the crater rim. Let's just say that. And so it created breccia, but also in the layers below. Uh, and by below, I don't mean the asteroid like the pictures I'm going to show hit on top, directly on top, but close to it. But these layers were down below, and so it created the effect in the deeper down layers also that were not fully rock. They were still it was still in the ocean bottom, still liquidy or clay-like. Okay, and the let me show also this. This cliff here is the Alamo breccia. That it's 100% breccia torn up, uh, a tumble of stuff, almost homogenized. That's why it created the cliff. It homogenized it, and so it gave the effect of almost like what is called a composite. Instead of layers like see below, these layers. Okay, but here those layers were destroyed and homogenized, so it formed a cliff that's more resistant. That's my interpretation. Okay, now the area of the pictures that I'm going to show that I had inspected this material, took pictures, and then I worked my way down. It took me a while to work down. It's very dangerous. It's not like what it looks. It's much worse than that. And so I worked down. Anyway, I came along here, working my way down here. And where I took these pictures was right in here. So notice that the pictures were roughly, well, let's say 100 feet, 200 feet strata depth below the asteroid breccia. Okay, so it certainly would have affected this material that back then would not, it was ocean bottom. In other words, like if you go out 10 miles out into the ocean and drill down, you don't hit the ocean bottom and it's rock. No, you're going to drill through a lot of stuff before you hit rock. So right here is where I took the pictures. So let's look at the pictures. And here's a picture of a Rayleigh-Taylor. Like this yellow would be less dense than the blue, more dense. And when it's unstable. And so this is a screen grab as they try to mix. So remember this. Remember that picture. I know it's kind of blurry. Matter of fact, let's do this. I'll let you watch it play. Okay, remember those shapes. Now that's a liquid. That's a model of a liquid. So now let's look at the pictures of the semi-solid. And so, in other words, well, why does this matter? Uh, it's because by looking at this and seeing this in nature, it can give clues as to past events such as earthquakes, where ground liquefaction can occur, or in this case, an asteroid hit, and the super, super astonishing beyond shock waves of earthquakes. Okay, so let's look at the pictures. Now, the material in question is down here. I know the cursor may be hard to see, but in other words, I didn't want to just show zoomed up pictures. And so there's the strata where I said I had worked down and was working along the back over here, and I came upon this. Now there's the material in question. I mean, it's perfect. It looks like it's been cut and polished. It was very unusual to stumble upon this. So the theory is this lesser dense material that when the asteroid hit, this was not fully lithified and it was affected by it, similar to an earthquake, and that almost like liquefaction occurred and this tried to rise up. See how these are trying to rise up and punch up through there like mushroom clouds. A little closer. And there you go. There's the Rayleigh-Taylor instability effect in Earth's strata, semi-solid or semi-solid material. There it is. And that should conclude this video. Is there anything I didn't? Here's another sketch from a video. That's a sketch that I grabbed from a video. And these are the layers just above. Let me show those. And the reason I'm showing this is because, well, if that material was lighter, well, what made it stay down there? Okay, so let's picture this, that this material here chemically could have changed and it could have become lighter because of chemical changes, bonding with water, whatever, who knows? And then these layers in a stable ocean environment, in the shallow ocean, could have collected on top, and it could have been a very somewhat stable situation where you actually had like oil floating on top of water. But that's an extreme case. Okay, this could have been a case where there wasn't that much difference, a little difference, but not much. And so then these layers accumulated just like what you see. But then when the asteroid hit, that little difference could have added up to a lot. And so you could be seeing an effect here of the Rayleigh-Taylor instability that you really wouldn't have seen unless there was some kind of shocking effect like an asteroid hit that brought it out. Okay, now that definitely concludes this video.